Okay, go for it.
Hey, welcome everyone. Thanks for joining from Spartan Series today. So today's a CAD workshop. What I'm going to do is I'm going to walk you through what the CAD process looks like for creating a prototype on 971, and sort of take you from start to finish from from a concept through the process with CAD, and hopefully we'll get at the end with a model that we could go and cut and make and turn into something. So starting out with kind of what are the high levels of what we're looking to do. We'll start out with an overview of sort of what methods of construction methods we use with prototyping that we're going to be designing towards. We'll frame up a mock problem statement here, go over what our goals are there, walk through some simple planning, and then bulk of it will be spent working in CAD and kind of showing you what that looks like in SolidWorks. So starting out with an overview on 971 for the past couple of years, we've done a lot of prototyping using 1/4-inch Baltic birch plywood. We like this material because it's relatively cost effective. It's very strong and durable, and it's quick to cut on CNC routers, and like the one that we have pictured here. So shown here, you can see a couple prototypes throughout the years where we've used this material in a various of different types of prototypes. So I'm going to walk through some of the what are the mechanical details that kind of make up these prototypes. So one of the key things here is that we're taking off-the-shelf parts or parts from previous year's robots that we have in the lab, and we're direct mounting those into sort of custom wood plates that we'll CAD up on relatively short time frames and get cut in short time frames. And so, but this is, we find this to be a nice balance of, getting geometries that are specific to the problems that you're trying to solve and the new game pieces and everything, while, being representative of the, getting geometries for the problems, and using components that we can translate through to the real robot, and also being a relatively quick process to do, because prototyping is about getting answers as quickly as we can. So see a lot of common parts mounted in with these wood plates. For the structure of the wood, we're doing a lot of gearboxes with just plate gearboxes. We'll use tabbed wood ribs to create structure between the two sides. You can see that between the top and the bottom of the gearbox, we use tab plates instead of spacers. This keeps us from, it's the reason we do this is because it's simpler to cut a tab plate on the router than it is to have someone make a bunch of standoffs. So it's all about really maximizing the speed there, and also it provides some pretty stiff structures. We'll use, to back up the tabbed supports, we'll use either long bolts or threaded rods with nuts on either ends to provide some compression there. Or in some places with lighter duty loads, we'll actually put holes in and use zip ties to just pull everything together. So for the exercise today, we're going to be using construction methods like this in the design. So going through what's the problem statement that we're going to work through today. So let's start with, let's say we have a shooting year, and I, kind of tune this towards what this year's game was. Let's say we're trying to build a prototype to test the accuracy of a single wheeled shooter at various distances and understand the impact of hood compression on shot accuracy. That's the question that we're going after trying to answer. So from this, we can kind of work through, and maybe we work through on a whiteboard what are the different requirements that this is going to drive into the prototype. So first one, game piece is, let's say, is a 7-inch foam ball. That's going to drive the dimensions on that. Let's say that we have we want to try a 6-inch shooter wheel. Different size shooter wheels are going to impact the shot accuracy, but we kind of maybe from the robot size, in the parts available and everything, we're looking to see what a 6-inch wheel can do. For compression, let's say we want to try 2 inches and 1 inch of compression as our two options here. We've maybe looked at what distances we want to shoot at and the wheel speed, surface speeds and everything, and are estimating maybe a 400 RPM wheel speed for that. We'd like this to be rigid. We'd like the prototype to be a solid prototype, because that will help us be able to get accurate shot data. So we would like, if the prototype is made well, we can then take data from the prototype and have it reasonably translate to what we expect to see with the robot when we build it. And then lastly, we'd like a feature that we'd like to be able to have some sort of feed belt into the shooter. So we're not just building a shooter, we're also building the feed system into it. And the reason to do this, and our reason maybe for doing this, is we're looking for consistency, and we're also looking for a little bit of safety to basically separate the operator from feeding directly into a fast spinning wheel. So those are the requirements that maybe we laid out. We'll start out the process with coming up with basically our goal, and then sort of the key items there. This here, I took a stab at sort of replicating what the sort of like the sketch on the whiteboard process and the walk through the lab and find random things process might look like. So over on the left here, we have did a quick sketch here. So here's our 6-inch wheel starting over in the corner. We need some sort of way to power the wheel. So looking at using a belt reduction on that. Did some math on that, and using a Versa a Falcon 500 motor with the standard off-the-shelf pulleys. It looks like we can get in the speed range we want with a 16 to 24 pulley reduction there. Kind of guessed on what belt size might be appropriate. Usually this is done by when you're prototyping, you try to put something together then. So what belt you use, and in this case, is going to be driven by what's in the lab. And then I guess I picked a Falcon motor here because let's say that's probably what we'd be looking to use on the robot itself. So if we can prototype with like motors, that gives us an edge up on that. And then the other reason for a Falcon is that it's got a built-in encoder into it, and so if we communicate to it over CAN, we can use that for velocity control, which is going to further increase the accuracy of our prototype. So good reasons there. So that kind of details out, I guess, the powertrain on the wheel. For the wheels themselves, let's say, we have a bunch of 6-inch wheels in our lab. I'm sure people have ones like that. Like, let's just say that there's, some wheels like, these wheels here, rubber, maybe, as grippy as we could get, but these look like pretty reasonable wheels. And then there's these ones would have a hub on there. So I guess thinking that we would use these as a sort of a dead axle, a live axle configuration, so that we can use the hex pulley to couple into the wheels themselves. So that's the center there. For the hood, different ways that we could do this. This is kind of what I sketched in here is based on some experience we had from the past season, but really looking to sort of create the curve of the hood by having a series of standoffs that will go between the plates to back up the left and to back up the flat surface that we'll have there. So a series of standoffs, and then take a piece of Lexan and bend that to that, and maybe we could just zip tie that Lexan onto the spacers. So this should give us a nice solid rigid back for the ball to react off of, be representative of something we could achieve on a robot, actual robot with design. And then also with the standoffs, we can adjust the position of the standoffs to maybe we have 2 sets of holes, so that we'd be able to, with some work, be able to adjust what the compression is, but not be recutting the entire prototype. And then for these axles, we generally keep some stock on hand for doing prototyping without having to start from solid round. So some of the Versa tube stock or spacer stock has some nice sizes that can have you could have a tapped hole. It's a tube axle that's sized for a tapped hole. And I guess we could use Thunder Hex, or I think in the past season we actually used some of the 3/4 tube axle, or 3/8 OD tube axle, which I think was sized for a 5/16 tap in the inside. So that's kind of pictured here. And then if we kind of sketched out here what a feed system might look like, I picked a one-sided belt here. Let's say we found 36 tooth 5mm pulley belts, and maybe I think 130 teeth might be the right distance. We can check that when we get to CAD. For this, we'll probably, thinking maybe direct mount bearings into the side plates, and then use Thunder Hex to go across and capture things. And then we'll use a variety of different, hex spacers and shaft collars to keep everything together on that. Then to power this, because it's just a feed roller or a feed belt, we're not not trying to looking to get a lot of speed out of it for this prototype, maybe the first iteration. So just powering it with a hand drill is probably sufficient here. So not going to spend much time on a motor or a gearbox setup on that, just because it seems like that'd be overkill here. And then kind of sketched through, thought a little bit about how we might make it stiff. So, sketched in a couple cross ribs here. So really, we could sort of create a box here underneath the wheel to sort of create some nice lateral stability, torsional stability here. Could put a plate in between the sprockets. And then also, we're going to get a lot of support from all of the standoffs that are going across the top. So kind of a rough plan right here. We'll see as we get further into CAD what that turns into. So this is kind of maybe representative of the planning process that we go through before we would dive into actually the CAD process with a prototype. Started out with, you have an idea of what we're trying to accomplish with this. We have a sketch, a whiteboard level sketch of how it is that we think we're going to lay everything out in CAD. And then also, particularly with a prototype, we've gone through the lab and we've actually pulled physical parts that we think are going to be used. Or if we don't have the physical part, we've got a plan of what we're going to go out and buy. So that's all that stuff has been done. We're going to do that before we get into CAD. So kind of rush through all that right here. It would certainly take a little bit longer if we hadn't done some prep work here. But now I'm gonna dig into the CAD side of that. So switch over to SolidWorks here. So I guess maybe, yeah. So now a little bit, kind of go over some of the practices that, with some of the modeling practices that we'll use to go quickly with prototyping. So the first thing that we're gonna do is that we'll use multi-body parts as a way to sort of create easy references between all of the different pieces. So multi-body parts will let us sort of, as we have these different panels in here, we'll actually model them all in one SolidWorks part, but be able to split them out per body later when we need to do the cam and actually get things cut. So that's the first thing. The second thing is that not actually going to model in any of the COTS parts unless, I guess, yeah, I won't do any modeling on that unless there's some question of fit or clearances that would actually benefit from having the pieces in there. That's just, we're basically, doing a pretty simple model here, and a lot of the deltas between what's in the CAD model and what we're going to assemble will be taken care of, with in a matter of a day. So don't need to create an extensive record there, and so really only need to be building out a full model as is needed to debug things. So those are probably the two main things. Yes.
Can you quickly explain the difference between a live and dead axle?
Yeah, so live and dead, it refers to whether the axle is the torque to the wheel is being transmitted through the axle, and then the axle is on bearings, or if the torque is being transmitted to the wheel through maybe a sprocket, plate sprocket, or that's bolted to the wheel, and then the wheel and sprocket assembly is on, or wheel and gear assembly is on bearings.
And then, if you could explain this briefly, can you explain why we went with the 16 to 24 reduction?
That was purely based on that previous slide where had said we pick some target range that we're looking to shoot at can do some simple math to estimate out what ball velocity we want, then you can from that back out what wheel RPMs we think we need to be at, and then from that I took the free speed of the Falcon and what sprockets where pulleys were readily available, and kind of picked a number from that.
Thank you. Great. That's all we have for now.
Thanks, Mir. So yeah, I'll go into I guess, yeah, on the CAD stuff. So we'll start out with a multi-body part. I guess the first thing is we got to pick which view, which piece we're going to start with. So I like to pick, that's the part that's got the most information in it. And really, from this, that's going to be the side view of this side plate. So we'll start drawing that out and kind of filling in those details on it. So start with a extruded base off the side. So first, kind of put in our wheel geometry. We have to pick something to fit to the origin. And I guess think through a couple of different things. I guess it doesn't really matter. Might as well put the wheel here, and we can just move that later if we want. Oh shoot, we're in millimeters here. Let's change that. We're in ISO. Sorry, let me, forgot to try that again. Sorry, I don't want to lose my work in the middle of this. Okay, hopefully this isn't, yeah, now this is the right template. Okay. So start out with a 6-inch wheel, and then we'll draw in the ball here, just so we can get a rough sense of size, what that looks like. So I'll put the ball in as a construction geometry, so that we don't have to see it much. So I'm putting in, just using relationships, and I guess I'm using shortcuts, so that's probably cheating there, to kind of show what things look like. I guess we could start, maybe just to get a sense of what things look like, we could put the hood in, so make that concentric, and then this here, so we'll assume that this is the inside of the plate, so that's, and then we'll draw the smallest of compressions. That's 5 inches. And then on the entry of that, would like to see, I think, I guess this was based maybe on stuff we were seeing last year, but probably have a funnel that's symmetric here. So I guess so far, let's see, got our wheel in there. Probably should put the motor in. I guess, oh, and then one thing in the pulleys in here. So what did I say? I said this was 24. So 3 millimeter pitch, so 24 times 3 millimeters divided by pi is our pitch diameter. And this is going to be 16 times. So one thing I'm realizing here is that we would like 2 different compressions here. We'd probably like to keep feeding the ball centered. So we probably want to actually move the motor back and forth. So that probably, I think the easiest way to do that might be to create a separate motor plate that gets bolted on, and then we can just take that extra piece and move it back and forth. So we'll guess what, maybe as I'm thinking out loud here, we will build this as a base sketch, and then we'll build the next piece, the pieces off of it. So here's our motor, and then the Falcon, if I remember correctly, it's like 2.55 or something. So we're going to want that to sit low enough that we're not going to intersect that bearing. So for the belts, what we'll do is we'll do a path length dimension on that. We had said, I think it was 45 millimeters. Okay, so that looks like, if we want the motor to clear the bearing here, that belt's not big enough. So we could go to the Vex Pro, and I said that was a 45. So maybe they have a 55. Or you could, it's not super particular what that is, but we do need one that exists. And yeah, we would probably, at this stage, I would have gone into the lab and tried to find another belt that would do what we needed. Let's see, we got that, and then we should plan out the feed system. This was 36 times 5 millimeters. So this is basically calculating what the pitch diameter of the belt is based on the number of teeth and the pitch. We're gonna do a similar thing on the. I guess we don't need to do a path link because the math is relatively easy on this one. So I guess I could. Sometimes it's easier to do to put it in an equation rather than just type it in, so you can come back and check your work later. So it's a 132. We have 36 teeth consumed by going around the outside. Then divide that by 2, and then times 5 millimeters. Okay. So now the question is, we have to think through like how much compression do we want on the feed rollers. Oh shoot, something's not happy here. There, now it's happy. So if we think about, if we have a neutral line of compression coming down here, I think that we're going to want, well, I don't know. I don't think we want to compress the feed roller as much as we're compressing the shooter wheels. I think here this is something that we would go through and determine by experimental. We could just take a belt and put it at different compressions on the table to kind of get an idea of what would be appropriate there. Something got constrained. So with it, something came over constrained. So I've shown the relationships, and now I can, yeah, that one got added in, inferred, but we didn't need that. So if it's maybe ½ inch of compression, I'm just guessing. So we got ½ inch of compression on the feed rollers. Okay. And then there's certainly going to be a distance here of how far up this goes. So what we can do is we can put a moving ball here and kind of get a sense of how it's going to transition. Or I guess we might as well just put it as the point where it first contacts. So ideally, we'd still like contact, driving from the feed roller system, and so it transitions over actively. So this looks not terrible here. We could probably define this in just to give an idea of where that sits. Because we're going to come back and we're going to drive everything off that, it doesn't matter terribly much. We're going to drive things off of this assembly. You can just pick semi-random numbers. Okay, so this is looking, I guess, looking pretty much like a shooter here. What are we doing on the core of it? Yeah, I think we've probably got the big pieces in here. Guess move on to getting that main plate in there, and we'll be able to piece through the different things that go in there. So I guess we don't want this as an extrude. We'll create one on top of it. So I guess even at the prototype level, it can be helpful to name your sketches so that when you come back to them, you don't get confused on what it is that you're doing. So now we're laying out the outside of this all. So this point here we have actually, yeah, this is going to be figured out later. I will not do this yet. That was going to be a bearing, but then I remembered that we're doing the plate on top of it. So these are going to be bearings here. Make them equal. Because it's wood, we typically just put everything on size, and that will end up as a press with the spring back and the cutting. And then I think we'll close this. Put some sort of sizing on it. for this exercise, there's no harm in actually just making a box. I don't see any reason to spend any extra time worrying about that. Probably, referencing things off of the location of what's there. So using the minimum dimension rather than like a center point. So you can select that by holding down the shift, and it will auto shortcut to picking the different arc conditions. This way, if we come back and let's say the 6-inch wheel was a great success or was a mediocre success on a prototype, and we want to try a 4-inch wheel, or we want to try an 8-inch wheel, and we want to basically recut everything. This way, if you go in and you update the wheel size, it will be relatively straightforward for everything else to auto update with it. So do that there, and then similarly up here. I'm just giving us a little bit extra margin there, particularly in the front. The wood goes and covers the wheel. That's probably safer, so that'll be good for us. And then here, we need enough room to fit the ball in there. I guess one thing we could look at is that we could look at the overall height of this. If we were super particular. If we are super particular, we might want to match this to be the height that we were expecting to shoot at. But I think that for now we can just this looks like close enough to a robot height that we will go with it. Okay, and then this I guess the last thing over here. Okay, I guess a lot less in this base sketch than I had maybe thought there would be. So I think that here you come into the balance of how much do you put in, just do an all in one sketch versus having a series of features. And I guess my strategy on this is to have things segmented to a reasonable level. If you have interdependencies between things, it's better to have. But the only real way to do that is to have it within one sketch. But if you have different features, let's say we have the hole for mounting the motor, and the wheel might be different from the holes that put in the hood. In those cases, I think it's better to do things in multiple features. That way, if you kind of change your strategy on how you do something, it's much easier to detangle what's happening and just go and delete the right thing and move on and put something else in. So kind of create a mix there. It makes the downside is you could end up with a really long feature tree. Okay, so now we're creating our first extrude. So here's where I'm starting to think forward towards our multi-body part here. And so, I've got in mind that, we kind of want everything to end up in space where we expect it to be. And so there should be a plane of symmetry down the middle of this, and we have plates that are symmetric to either side of that. And so what I'm going to do is I'm going to, on the from condition, instead of starting on the plane, I'm going to do an offset, and do that offset by the width of, or half the width of what we expect the prototype to be. So 7-inch ball, I'm just going to guess that we make it 8-inch wide. That seems like enough width on either side of the ball so that we're not going to run it, we're not going to be impacted by the side walls of the prototype. So that means that we'll offset by 4 inches. And then, then it's going another 1/4 inch beyond that. And so I guess the wood is such that it's close enough to 1/4 inch that we just plan off of a 1/4 inch and use nominal on that. Okay, great. Because it's the first one, I don't have to worry about any of the features there. So that kind of put that plate where we'd expect it to be in the robot. So I guess looking pretty good there. One thing I was thinking through, I figured next we can put in some of the spacers there. Should probably think about and plan out in this sketch here what hood angle we're going to go to. So here's where we're going to do our math and make some sort of trajectory assumption on what's the longest shot we want to make. Let's say that, I don't know, 15 degrees. That's a pretty far shot. And really, I guess my other thinking is that err on the side of having it be too much. And then what we can do is we can dial that back as we want. And sorry, but by that I mean, if we put in extra holes so that the hood angle goes super far, we make the Lexan plate, we screw it on, we decide that that's it's shooting too low, and it's out of range of what we want to do with just sort of popping up the prototype front and back. You could always take out some spacers and trim the Lexan, and then we'd be good there. So 15 degrees, we'll go with that. So now I'm going to put the holes in for the feature here. And, putting in holes, it's generally nice to use Hole Wizard on things. Particularly, I'm going to use Hole Wizard here because I can actually use a linear pattern to simplify some of this. So, so what I'm going to do is we're going to put a Hole Wizards into here. If I remember correctly, it is 5/16, and we'll do close. So now I'm going to kind of sketch out how things look. So we have our stack up here. If I remember correctly, it's not the spacer is actually 0.375 OD. Oh, that does not look right. Maybe it's a. Yeah, so that must be, I'd have to look at the stock. It doesn't really matter for this discussion. Let's say it's a 1/2-inch spacer. So 1/2-inch spacer, and it's going to be, we're going to start it on this end because I think it helps us out in the end. And then we want to plan for our Lexan. And the Lexan is going to be 1/8 of an inch. Okay, so here's where our first standoff is. Now, instead of just putting in a bunch of holes, we can actually use a curve-driven pattern to generate all of those curves for us. So I'm going to put in 2 lines that we're going to put in lines in the sketch that are going to form the path that we're gonna have our holes take. Shoot, that did not define it yet. There we go. So we want the holes to be distributed along this line evenly, or we'll get to figure out exactly what. So I think I need to make that construction to do that. Okay, great. So put that through, and then we'll put the holes along it. So so linear pattern, curve-driven pattern, and then the direction. Oh shoot, I want to select the sketch.
We have a question asking, why did you make the hood construction lines?
I guess I could have gone either way. I at one point I thought I'd make it that we were going to make that our boss extrude, so it was better to have things construction lines. But I guess it doesn't really matter here. So I'm going to go here with equal spacing so that we can have when we make the Lexan piece, I think it will be easier to get the holes to all line up. So make this, I don't know, let's do it 0.5. Oh, that looks too much. Or 1 inch. Yeah, sure, 1 inch spacing looks fine. Nope, that's not what I wanted. So yeah, this is putting holes that line up over the path that we want to take. That looks pretty good there. And we can now use the same strategy to go in and put the holes in for the larger compression. So might as well I guess might as well go in and do that now while we're here. So 5/16, yeah. So I guess in this case we got to draw in the curves again. So these, yeah, we know that this is going to be the same radius as the line that we had before, and just offset in some. This actually will start at the same height. And then this is going to be offset over by, shoot. This is going to be offset over by 1/4 of an inch. No, half of an inch, right? Because it's going to be 1 inch of 1 inch of compression the motor will move by half an inch, and this will move by half an inch. Okay, and then we put the other one in. Yeah, if we wanted the extra, like an extra spacer out there, we probably should, go in and increase the. If with the 15 we thought was a very precise number, we should probably increase that a little bit. But that's neither. I don't think that's a problem for us right now. So now we can go back and create a curve-driven pattern. Yeah, I've going and selecting from the feature tree instead of just selecting on the sketch, because if you select from the sketch, it will draw up, it will pull in, if you select from the sketch, you'll put you into having to select each of the segments and building a contour from that, and that makes it harder to update if you add add a new line segment or do something like that. So it's more robust to have the sketch in there. Great. And so, here we see that we get one more hole out of it, which makes sense because our path length is slightly longer. But the spacing between them should be roughly the same. So when we cut the lex, well, it is the same on the curve. So, but the holes in the lexan will be roughly the same. So that should be, that'll be nice for us later. Cool. So we've got the mounting holes in for our spacers. And, at this point, I think that the temptation may be to actually put spacers in here. To kind of visualize what that looks like, but that's just extra work, and I'm going to be lazy. And so we'll see what it looks like with spacers in there once we actually go ahead and build it. If we really thought it was critical, we could do that here. Cool. And so now we're going to go ahead and let's see. We got the hood. Why don't we attack the motor next? So now this is going to be our first point of a multi-body part. So what we want to create is we want to create an assembly, or sorry, I guess we are creating an assembly. We want to create a part in here that's going to mount and hold the motor, hold the wheel on the motor, and then we'll cut a pocket in the assembly, and we'll have two different mount spots for it. So let's go ahead and put in the first one. So we'll extrude boss space off here. So this have our bearing hole, and then our motor hole, and we're just going to use exact center to centers, which I guess we made that decision earlier. And then we have our mount holes for our Falcon. This is something where I guess I probably should make these. It's better to use maybe Hole Wizard to decide, or it could be better to use Hole Wizard. I'm just going to put them in here so it's one less feature, and because I know what the sizes for their 1032s. We'll do a close fit. So in general, our preference, I thought I got that one. General, our preference is to kind of use Hole Wizard whenever we can, but we'll kind of take a shortcut here because this model's not going to live very long. Okay, so now we're looking at, we have, we're going to have the plate that everything gets mounted to. I guess it doesn't, the plate doesn't need to be much bigger than the hole. We're going to, yeah, I guess we can always come back and fix it later if we're wrong. Yeah, sorry, just thinking about what to do here. And then, yeah, we'll make it centered. So selecting the midpoint here and then just make them vertical. I guess I could put a construction line in, but doesn't seem necessary. Yeah, planning this out. If we put the yeah, we'll just make this a little bit. I'm just thinking that we'll make the holes above where the motor is. That will be, so it'll be a little bit cleaner there. So that. Yeah, but sorry, the mounting holes will go above the slot that we cut out rather than to the left and right of it, which means that we don't need as much margin on the left and right. See what this looks like. Okay, I think that's all defined. Great. So now this is our first part, our first extrude that is going to be a separate piece of. So we want to basically this is where we get to the multi-body part. And so you can see that it looks like it's starting to look like 2 plates stacked on top of each other. Really, the way to create multi-body is you just unclick the merge results, and now it doesn't extrude. But if you go here, it added a folder for bodies. And so if we isolate, per body, we can see this is one piece here. It hid one of the bodies there, and we can exit. And then we can select the other guy. We can isolate on it. So really, what we've done is we created 2 parts in one part file, and that's going to let us create robust references between them. I guess you could accomplish the same thing in an assembly with in-context parts. But I have found that to be, as soon as you start getting out of the context of that master assembly, it starts getting hard to manage. And so this is the easiest way to sort of keep all the bad things contained in one spot. So now we can put the hole wizard in for the mounting holes, because we actually, we want the mounting holes to go through both of them. 10. We standardize pretty much on 1032s. So I guess, well, this is probably a tedious way to do it. We just want them all spaced in evenly. So just put a bunch of construction lines in on that. Great. And then, okay, I guess the default was already go through all. So that made one set of cuts there. Now we can go through and we can cut out the box, the clearances. So we want to make sure that our pulleys fit in there. That would be pulleys and our screw heads. So this is, so yeah, I'm kind of just picking arbitrary dimensions because it doesn't really matter here. And then on this guy, because we're going to be sliding, oh, actually I got it backwards. The motor is going to move out. So this is actually, so that's 0.25, and then we'll add, make that 0.75. Great. Okay. And then, so here, actually here, there's no ambiguity about which body it is, but if we wanted to make sure it only cut through the right one, we could go through and just select the body and instead of letting it auto select. Yeah, because we're putting a hole on the inside, we need to make sure to add our fillets in there. Yeah, 0.1.
We have a clarifying question asking.
Yes.
Is the offset distance for the hood standoff hole supposed to be 1 inch? If not, wouldn't the prototype test for 2 and 1.5 inch compression instead of 2 and 1?
So yeah, we have ½ inch. So we have ½ inch of, we move the hood out by ½ inch and we move the motor over by ½ inch to go to the second one. So the combined should be a 1 inch of delta. So that's actually, this is a feature that we're putting in here. Let's see if this will work with just a linear pattern. Shoot, why is this? So we're putting a second set of holes in there, and we just want it in this one. Great. So that looks like the right thing. So if we want to swap from the 5 inches of compression to the 7 inches or 6 inches of compression, we'd have to take this plate, move it over, and then we have to move the standoffs out. Cool. So I think that's should be all the hardware we need to get the motor to spin and have the belt and stuff. Now I think we're onto the structure here, and so this is where we're going to think about it. We're going to add some more parts in here. I'm going to go ahead and build that box out that we sort of sketched out over here, and thinking through how to simplify it, what sort of shortcuts that we can take. I mean, we're gonna have a lot of symmetry in here, just to create that box. So, well, let's just take a stab at it. Yeah, we'll figure this out. Okay, so I'm gonna start by just drawing in we'll start with this plate here, this vertical one, and then we'll go ahead and we'll put in the cross one. So I'm gonna do an extruded boss base off. Oh, not that one. One on the inside. Actually, why don't we do it off? Do it off the right plane. So I'm only going to draw half of it because we know that we need to mirror it left and right. So I'm going to draw this. Yeah, why not? We'll go all the way down to the bottom. That'll give us maximum sort of stiffness there. This guy is going to be collinear with the line that we drew previously. We need to make sure this doesn't intersect with stuff up here. I can't really see it doing that. It's going to need to clear the wheel. So I guess we might as well just dimension off that. Yeah, once the ball gets up here, it's going to start going really fast with the wheel. So we'll make this 0.75. In general, kind of put dimensions down. If they look close enough, just round it to the best fraction, or whole same number. So now we'll use I'm going to use the end conditions again. So from we'll do from the sketch plane, and then up direction we'll do up to surface. This gets back to making the model robust. If someone went in and changed the width of the shooter for like a second generation, it would automatically update everything here. And then because we want it multi-body, we will not merge it. Okay, great. So now we've got that there. I'm actually going to isolate this body so that we can put those tabs in there. So now we're going to go in and we're going to put the tabs in like we have over here. So kind of creating a square cut, and then we have to relieve out the corners on it. So I'm going to put extruded boss base on this side, and this will be. So we'll put a couple in here. The tabs not going to go all the way to the end, so that there's something on both sides for it to interlock into. It looks like 4 looks like a reasonable number here. Like to make them all equal. Two inches long seems fine enough. 1 inch from the bottom. And now I'm going to go through and going to just put some sketch relations to even everything out. I guess I probably could have used a pattern, but at some point it's easier to just commit to something and do it. Particularly with this short time frame prototype work. Okay, great. Everything looks defined here. And then this, yep, it's already got it, 1/4 inch, and then it should auto select to the right thing, but we can just double check that. Okay, we've got that. And then what we can do is, we need to put the cuts into the other place. Well, so conveniently, that extrude that we did, we can do similarly, just do a cut off of the other one. And so this is the beauty of the multi-body, is that we can auto-reference everything together. So now we have cuts in one and tabs in the other. Now let's do the part where we do the sorry, not mirroring. Do the relief cuts in it. So just gonna start with, I guess not. Yeah, we'll do relief cuts then because we're gonna pattern things and it'll be easier then. So now take this guy and let's see, we'll just isolate it out. So need to put reliefs in all of the corners, yeah, so that we can cut them with a router. So this, with great practice, you can get it so that the relationships all go in at the same time, which makes it pretty quick.
Someone asked, how do you select only the construction line and not the other sketch?
With which part of the assembly?
I'm not sure.
Only construction line. I think the stuff is so far has just been like auto snapping. Like I haven't had to worry about being super precise on selecting things. Maybe ask a follow-up question. You can always do like right click, select other. That's all. You know, something in here is tangent. Darn it. That is obnoxious. Well, and then this diameter that I've chosen is just what we use for end mills. Here we go. That's our culprit.
A follow-up question is, when you placed construction lines on the edge of the part, how did you only select those to create sketch relations?
When I place constructions, at which step was? Sorry, that took longer than it should have. There's the relief cuts. I'm sorry, I'm still not following that one. I'm gonna take these, and because we want a box, I'm just gonna linear pattern them over. And here, this is not the cleanest. I guess we could clean this up, but just gonna guess at the dimension until it looks right. Okay. Great. And then we want, to create a box for strength. We want to have a cross-referenced on it. Trying to think about, does it really matter where we put that? Sure, we'll do it in the middle of the tab. It doesn't matter. So gonna do a similar thing here. We'll start there.
A question was asking about when you were making the rectangles for the tabs and to make the spaces in between them.
Oh, how did I mean, I think I just manually selected on them. I didn't have them go over any of the, so none of this construction lines went over the non-construction lines. That helps.
Okay, thank you. I guess that.
We'll see that again, I guess, and maybe it will make more, or be clearer there. Okay. Oh shoot! It did not unclick undo. Do not merge results. Yeah, I guess this is the slope part that is not terribly interesting. But oh, wrong direction. That did not go well. Oh, we had flip-sided cut on. Okay. And I guess in this case, I don't need to go through and necessarily show doing the reliefs on that. We'll do that if we have time at the end. Then here, oh, shoot. Gonna do a tab off here. So because it's a midline, we'll just do it. We'll put one in there, and then because it'll get mirrored, it'll get sent over from the other side.
Someone is asking if you're planning on making relief. Was it relief cutouts on the tabs themselves as well?
Yes. Yeah, I'll do that. I guess I'll do that on one of them so that we can see that all.
Okay.
So here I'm going to be lazy. I'm just going to take the same same sketch and use it for putting the other side on. So we can do that by modifying the start conditions. Great. Yep. So that's a great point. Let's see. On this guy here, we need to put relief cuts in it. So I'm going to go through and we'll do extruded cut on that, and then typically put him in on this side.
I have a SolidWorks setup question, which is what preference do you have set that allows you to select a feature or plane from the design tree and view where else it's referenced via the branches?
That's a great. There's a menu that had a lot of settings, and I just clicked all of them. So I think.
So just play around with things.
I think maybe it's this stuff: dynamic reference parents and dynamic reference children. Yep. Yeah. So this is that relief cut that whoever put in that comment was right. We do need. Shoot, oh, wrong direction. There we go. Okay, and then we can put this cut. This guy needs to cut. So at this point, I think we're set up for everything. Oh, no, I need to do a pattern down here. In this case, we'll just mirror this down. Mirror the cuts down. That cut. So I think everything is, and then I think everything's set up so that we would like this part would work over here. If we were really, I guess we might as well just put the piece in to help ourselves out. So these two pieces should be same top bottom. We don't necessarily have to put them in, but we could put them in. I think that the other thing that we need to do here is we need to create a mirror left and right to be able to make the part. So mirror, and we'll do bodies to mirror. So the reason I do bodies to mirror is because if you go back and you add more features to the bodies, you don't have to like reselect everything. So this is, and I think we might have to do it per, well, let's see if it's happy. Nope, that's not what we want. Merge solids. That give us our bodies. Yeah, they cut the two separate bodies here. We could go through, yeah, we could go through and we could like actually move this guy over here. Well, I guess why not? Insert features, move copy, copy, translate by, oh, translate in Z. I can't remember, it was like 5.5 or something. So that's, a quick way we can just kind of put that piece in place. Really, if we're going to cam it, we're not going to actually do that. So, and then I think the last things that we probably need to put in here, well, besides we probably want to put a rib, somewhere over on this side to strengthen the belts as things come in. And we could probably put one down on the bottom if we were super worried about that. I think, yeah, you also could like take a 2x4 and put a 2x4 across and stiffen it. It does, we don't need to be super precise here. It's more about, what is easy to do in CAD that's hard to do later. Let's get that stuff done here, then let's get it to the fabrication so we can get it cut. Last thing that I want to put in here before we probably call it quits is want to put in the compression members. So what we'll do is we'll just put a whole wizard. We have, I guess, so we have some general 1/4-20 rods that they're a threaded rod, all thread, and we'll use that in a couple of places. But the idea is that let's put these wood members under compression, and that's what's going to actually create the strength of the pieces. And this is just some clearance, but I don't know how much. It doesn't really. Oh shoot! Okay. Oh, that's just a little close to that tab there. So let's increase that a little bit. Yeah, and also compressing, compressing right here, I might want to move the tab or move the, yeah, maybe having the tab intersect here wasn't as good an idea as I thought. I don't know if we can just quickly move that up here. Because we'd like to put that compression inside of we'd like to put that compression through not through an exposed tab, but actually through a part. That's just too close. It's closer than we need to be for a prototype. Yeah, it's maybe better, but I still don't like that. Okay, so that maybe moves it up some. But now we're like, when we put those rods through, we're going to be compressing through the meat of the piece there and getting some nice junction between the two of them. We could probably overkill it and add some extra holes in now if we wanted. I think I'm looking around at what we've got here. We could, we're pretty close to being able to cut something and be able to get this up and running. Probably, we could go back to our requirements and look at how we're doing on that. So yeah, I definitely have 7-inch wheel. We've got 6-inch shooter wheels, 2-in-1 compression. Looks like we're set up for that. We got those gear ratios. Probably should be rigid enough, and if not, we'll be able to fix that. I guess the most important part is probably the fact, the hood construction here. This is, we have this made pretty rigid there, so that it will get a nice solid foundation there, and then we can add in stiffening like 2x4s or things if needed or based on what we observe. And then kind of going through here, you can sort of see how this sort of sketch sort of translated into a SolidWorks model here. If I think about what's left between here and actually cutting a prototype that we could use, we'd have to go in and we have to model in a Lexan plate that's got the holes in it, so because we probably want that just cut out on the router to make things easier. We've got to go in and finish adding in all the reliefs. I'd probably go in and add fillets around everything using the auto fillet, just because it makes things easier to cam and also ends up with less sharp edges. We talked about adding in a stiffener over here or somewhere around here, or I guess, or the 2x4, either one would work. Do that. I think that covers pretty close here to being able to have something that we could send over to the router, get cut out, and then be up and shooting in an evening.
Before you wrap up,
yep.
Quickly, would you mind sharing a few of your favorite keyboard shortcuts and mouse gestures in SolidWorks?
I haven't really gotten into the mouse gestures much. On keyboard shortcuts, I guess I use all of the relationship, the vertical, horizontal, equal. You saw me use those a lot throughout the time there. Use those are like hardwired into like Alt and then the V, H, and those things. Then there's use construction, switching between construction lines a lot. Use dimension, so just like I've shortcutted in Smart Dimension to D. I think I used V for viewing and hiding sketch relationships a bit. That was I think those were the main ones that I was using here. Oh, and then S is another interesting one, in that this is S just pulls up a shortcut menu that's got, I think it's hard coded into that, but it's just got some of the handy, the most used features. So that's how I'll get to circles and squares and things. I don't have them shortcutted out from there. And then, yeah, definitely, we didn't use any measuring here, but definitely use a lot of that. Then, yeah, I guess last wanted to wrap up with, this is a picture here of a prototype that we made this past season, using, kind of, I guess I cheated, I worked backwards. Using a lot of the things that we talked about here. And yeah, you can see that we've got, I guess we have a bearing plate that we can move back and forth. We have some ability to adjust the compression and where the motor is. We've got some box construction here to stiffen it up. And then, here we have it connected up to a robot, so that we can control get the speeds controlled on the shooter wheel, and be able to get to collecting data and answering the question of, is this a good design or not? So. Any other questions, Mira, before? I think that was pretty much all I had, unless people have some questions to bring in.
We don't have any more questions right now, so I think you're good to wrap up.
Okay, great. Well, thanks everyone for tuning in and checking out this Spartan Series session. So we're going to be having more sessions throughout the week, so please be sure to tune in to the other ones, such as tomorrow we're going to have a session on effective organization and workflow management. So should be a lot of great content. Hope you get a chance to tune in. Thanks.